Welcome everyone. Today I'm going to present our work on neural termination analysis. My name is Julian Persat and this is joint work with Milko Jakobe and Daniel Kröning. Program termination is concerned with the problem of whether a given program terminates on all possible inputs or not. Here we have two problems. On the left hand side we have a program that terminates on all inputs because regardless of how x and y are initialized, we either enter the loop body and increase x until x is equal to y and thus exits the loop, or it doesn't enter the loop in the first place. On the right hand side, however, we know that if x is larger than y, initialized larger than y, we enter the loop body and we never exit it again, as x will always be increased and y stays the same. This problem of the program termination is undecidable and is an important problem in a lot of different models of computation. Usually, program termination is shown by providing ranking functions. In particular, ranking functions are sets that map program states, in particular consecutive program states, to elements in a well-founded set where two consecutive states are decreasing. This means that at every step they're decreasing and they're bounded from below, as imposed by the well-foundedness. Hence, there cannot be an infinite descent, or if there were, the program wouldn't be terminating. But since we are in a well-founded set, this cannot be the case. As an example, consider the program from before, and we create this control flow graph, and we can see that the provided ranking function here, y minus x, is in fact decreasing at every step here whenever we reach this loop head. So when we reach this loop head and we loop through again and again, this will always decrease by 1 because x is equal x plus 1, so y minus x in time step t minus 1 is always greater than y minus x in time step t. Our idea is simple, namely we want to use machine learning to generate ranking functions, and we use execution traces as training data. Subsequently, we want to use formal methods to verify that our ranking function candidates are in fact correct. This is all based on the idea that checking a proof is easier than finding the proofs. So we use machine learning to find proofs, and then we use formal methods to check the proofs. Our method is split into 3 steps. First, we generate execution traces, which will constitute the training data. Once the data is generated, we use machine learning to produce candidate neural ranking functions, and then we use verification procedures to check whether these candidates are correct or not. So first, given a program, we identify the loop heads. In this case, the loop head is at line 2. Subsequently, we will run this program with a lot of different samples. For example, we initialize it with 5 and 10, so x equals 5 and y equals 10. And we execute this program, and every time we reach line 2, so where the loop head is, we take a snapshot of the current memory contents for x and y. So for example, we run this program. In the first iteration we are at 510, we reach it, then we go through the loop body, and then we reach line 2 again, so the loop head, and x is increased by 1. And we do this until we reach a certain threshold or the program terminates. We do this exact procedure with a lot of different traces, with a lot of different inputs, sample inputs, so we sample this. So for example, here we have a sample with 13 and 8 where we don't even enter the loop guard, hence the trace is basically non-existent, or also with negative numbers and large numbers, and it doesn't matter, we just run this program with all different kinds of input data and trace it. Then given these traces, we generate our dataset. Our dataset is essentially a sliding window of size 2 of these traces. So here we have 2 consecutive states, and these constitute our first training pair. 510 and 610 are 2 consecutive states that constitute 1 training pair. And we have this we create the sliding window of all our execution traces. And we create this, and in the end we have all these pairs of states, and these constitute our training data. Once this data set is obtained, we can move on into the learning phase, where we constitute that the learned model is in fact our ranking function. And this means that a model M maps the vector representation of a state to a well-founded set. Hence, this model, because it has to be a ranking function, has to satisfy that it's decreasing by a discrete amount for 2 subsequent states and is bounded from below, meaning that training a model is equivalent to synthesizing a ranking function. These two conditions are imposed by, first of all, requiring a ReLU as an output, meaning it is always bounded from below by 0, right? Because that's how a ReLU works. It's 0 for all negative numbers, and once it's positive, it just is the identity function. The second one, the decreasingness of a ranking function, or in our case, the ranking model, is imposed by the loss function by using this margin ranking loss, where 2 consecutive states, so pairs here, O and O prime, need to be decreasing by a discrete amount delta. This works as follows. So here again, we're given the training data obtained from the traces as we've shown before, and we have a model here, and we essentially use all our training pairs to train our model for 2 subsequent states. So here we have 5 and 10 and 6 and 10. This constitute f of O prime and f of O, and we impose that they have to decrease by this discrete amount delta. And we do so for all possible for all states in our training data. After this model is trained, we use formal methods to verify that, first of all, our model or neural ranking function is decreasing at every step and bounded from below. And the important thing is that this has to be the case for all possible states. So not just for our training data, but for all possible states, because that's what termination is, right? And we do this using SMT by encoding the bytecode and the ranking function into an SMT formula and using an SMT solver to show whether or not this is indeed the correct ranking function for all possible states. We implemented these methods and you created an experimental evaluation that I'm going to present now. So the first question that we asked ourselves is whether neural networks can be used to formally prove termination in general. We obtained 2 problem sets from the termination competition and the software verification competition, and there we had 2 problem sets, namely the approve 09 set and the termination crafted lit set, and these both constitute problems from literature. Our tool was able to solve 76% of all problems, and other tools such as approve was the winner in this category and proving almost 90%, Ultimate with 86%, and then Dynamite with 70% of all problems. Note here that while we're not in the first or second place, I think we do we perform comparably and even outperform some other competitive tools, such as Dynamite. And the next question that we ask ourselves is whether neural ranking functions advance the state of the art in termination analysis. For that, we looked at problems such as the following, where we have a nonlinear loop condition or loop guard. However, the ranking function is indeed linear because the loop body, as you can see, only exhibits linear behavior. Such problems are actually solved by Dynamite. However, tools such as Approve and Ultimate that translate this entire program into a different model of computation are unable to solve this problem. Our tool is able to solve it very quickly, and so is Dynamite. Similarly, when we have disjunctions in loop guard, so here again we have nonlinear behavior and we have a disjunction over the loop guard, so we have 2 different loop guards. None of the compared tools are actually able to solve it, not even Dynamite. And our tool, new term, immediately produces the following ranking function and thus solving this problem actually. We use these 2 techniques, so disjunctions, for example, as well as nonlinear behavior in the loop guard, to generate a problem set of 14 problems, of which our tool is able to solve on average 13 problems actually. So sometimes it does solve every problem, but in some cases fewer than 13 problems. But on average we are on 13 problems. Approve is able to solve 3 out of these 13 problems. Ultimate is only able to solve 1, and Dynamite is able to solve 7 out of these 14 problems. The last research question we asked ourselves is whether neural ranking functions scale in terms of the complexity of a given program. In particular, if this constitutes our neural ranking function, we were wondering if increasing the neurons in the hidden layer will lead to any better results. And it turns out that while increasing it in the beginning, so going from 1 hidden neuron to 2 hidden neurons, is indeed leads to an improvement. Going any further will only lead to very marginal improvements, and then subsequently might even decrease the improvement, the performance. However, we are able to come up with a certain problem, namely this problem where you have k disjuncts, where it turns out that we need a neural network of at least k hidden neurons to show this terminating in the first place. So here, if we had fewer than k neurons, it actually wouldn't be able to show anything terminating. So in conclusion, I've presented our method of neural termination analysis, where we use execution traces as training data, and network training essentially constitutes ranking function synthesis. This performs very well when we have disjunctions in our loop guards, or we have non-linear loops with piecewise ranking functions, where loop guards have non-linear behavior, whereas ranking functions for these loops are completely linear or piecewise linear. Thank you for your attention.